Welcome to the meeting of the West Michigan chapter of the American Scientific Affiliation this evening. We're very glad that you can be here. We're really glad we have as a guest speaker Tom Ackerman. I'll introduce Tom in a few minutes. My name is Ralph Sterling. I'm the president of the local chapter, and you'll hear more about that in a few minutes. I'd like to briefly open with a word of prayer. Lord, we thank you for your presence with us tonight. We thank you that we can observe the changing of the seasons and see the effects of this wonderful planetary system that you've devised of linked atmospheres and oceans and lands. We thank you for your sheer generosity in creating this world and making it so abundantly rich and so beautiful. We thank you for your abundant generosity in creating us too, and stamping us with your image and permitting us some ability to peer into your creation and enjoy it. We pray that you bless our time tonight. We do think about the evils in the world, Lord, and we do especially think of nations like India and Brazil and Turkey that are experiencing huge upticks in the coronavirus, and we ask for your mercy that might be dampened. So I thank you once again, and I ask that you would bless us as we interact with Tom in this evening. We pray this in Jesus' name. Amen. So I'm going to introduce Dana Oleskowitz, who is the local chapter coordinator. Dana will tell us a little bit about, for those of us especially that aren't acquainted with the ASA, she'll introduce us a little bit to its history and function. So Dana, I'll let you take it for the next few minutes.
Sure. Good evening. My name is Dana Oleskowitz. I'm the local chapter coordinator for the ASA. So I work on staff. My background is in aquatic ecology. So this topic is of great interest to me. So I'm pleased to be here this evening. So I just wanted to give you a quick overview on the American Scientific Affiliation, who we are and what we do. So the organization was founded in 1941. It is international. We have members from really all over the globe. And many of our outreach events now, because we can do it virtually, we really have reached out to a good number of countries with this new platform. So that is something that we're very pleased with. We are a group of scientists and theologians with an interest in the faith and science intersection. We are Christians, and so we are interested in how the universe started, how it operates, but also why it exists. So our statement of faith is here on this slide. God is both the creator of our vast universe and the source of our ability to pursue knowledge that's honest, and open studies of both scripture and nature is mutually beneficial. We have two main sources of information that we do outreach to our members, and that is through our quarterly journal, The Perspectives on Science and Christian Faith. We also have a magazine that's done quarterly called God and Nature that has essays and photojournals in it. And then we also have implemented on the second Saturday each month, we have an outreach event called Diving Deeper Discussions. And that is led by Randy Isaac. So we have one coming up in May, early part of May. So please be on the lookout for information on that. It's really a nice way to interact with professors and theologians, scientists in the field of science. We also have our local chapters, and that's really the function that I provide, is making those connections between the chapters and the national organization. We have 36 chapters across North America. We also have the Canada chapter. So collectively, there's 36. We also have 5 student chapters at universities. Each of those local organizations will get together either bi-monthly, twice a year, once a year. Some are more active than others. So one of the things that I do is reach out to those groups to encourage the engagement. And now that we can do things by Zoom, what we're finding is that people from all over the United States can attend these local events through the virtual platform. If you're interested in our membership, we have full membership is $85 a year for scientists, and we also have what's called an associate membership. For those that are non-scientists, they may be theologians or people who are interested in the sciences that would like to participate in our organization. We also have a student membership, and that is free for a basic membership. If you're interested in a premier, that's $20 a year, which also includes voting rights and a printed copy of the journal and free registration at our events, particularly the annual meeting. And so we encourage you to take a look at that. You can go to our website and use that promo speaker. Thank you. Thank you very much.
Thank you very much, Dana. I need to introduce Derek Sherman for 1 minute. Derek's going to comment on the means by which some of our Calvin engineering students can get credit. Derek is our webmaster for our local chapter and generally our tech guy. Derek is professor of computer science at Calvin College. And we have two other officers, Gail Ermer, who's our treasurer, professor of engineering at Calvin, and Ryan Beebe, who's our vice president, who's professor of biology at Calvin College. So Derek, if you want to take it for 1 minute.
Yeah, thanks, Ralph. And just a reminder to all the engineering students here, I hope you noted the free membership that you can get as a student with the ASA. So you may want to check that out. But for the engineering students that are here, I know you would have come anyways, even if you had no points offered. But since you're here, please look in the chat section. I'm pasting there a link that I got from the engineering department for you to fill out a form to get a point for attending this seminar. So just look in the chat session for that link where you should be able to find it now. Thanks, Ralph. We'll pass it back to you. And we're very glad that the students were able to join us. So thank you for joining us tonight.
Yes, great. Well, what I'd like to do next is introduce Tom Ackerman. I've known Tom for quite a while, and I've known of his work for a lot longer. I first got acquainted with Tom's name in the early 1980s. Many of you, or some of you at least, will know of the phrase nuclear winter. Well, the phrase nuclear winter was engendered in a 1983 paper with 5 co-authors, 3 from NASA Ames Center, where Tom was located at the time, on this scenario for what would happen if there were multiple nuclear explosions around the Earth and it threw up dust in the atmosphere and so forth. At that time, Tom was a planetary scientist interested in planetary atmospheres. Subsequently, after working at NASA Ames, he went to Penn State, where he continued to author papers on planetary atmospheres and even atmospheres on the early Earth. So he had an early reputation there. But about that time, Tom got interested in clouds and their effect on climate. And as he got more and more interested, he realized that we needed a lot more really accurate data. And he got sidetracked, as it were, into thinking about how do you actually get measurements on clouds. And he developed techniques for doing radar measurements of clouds. And as such, he continued his work there at the Northwest National Laboratory in Battelle, Washington. Eventually, he went back to the University of Washington, from where he had gotten his PhD years before, and became director of the Joint Institute for the Study of Atmosphere and Oceans at the UW, which is actually more broadly part of a consortium of several universities. He's received the NASA Distinguished Public Service Medal, the Leo Szilard Award for Science in the Public Interest, and he's a fellow of both the American Association for the Advancement of Science and the American Geophysical Union. So we're very grateful that we can have a good friend here, a friend of the ASA and a friend of us tonight, and a friend of the Earth to talk about climate of our planet. And I'll let you take it from there, Tom, if I haven't failed to do you justice, I hope.
More than adequate. You failed to point out that I did get my degree from Calvin, my undergraduate degree in physics. for which I was deeply appreciative. And I really want to make a shout to Howard Van Til, who was my mentor and guide along the way. And I wouldn't be where I am if it were not for the interest that he took in me as a physics student.
Nice.
So I have great fondness for those memories. I also want to point out that I may dive off for a drink now and then. It's a beautiful spring day, and with beautiful spring days come beautiful amounts of pollen. And I find my throat scratching away, so I hope you'll bear with that. So let's get if you have questions, normally if I were speaking to you live, I would say just wave your hand and I'd do that. I find it a little disconcerting to get voices out of the ether. So if you wouldn't mind, put a question in the chat and we'll try and come back to it when I'm done. But I do find it a little shocking when my computer suddenly starts talking back to me these days. Okay, so let's get going. One of the problems of dealing with a complex problem in a short amount of time is it's like this little guy skipping stones across the water. You just kind of hopscotch from plunk to plunk to plunk to plunk, and you don't have time to deal with anything in detail. I apologize for that, but this is a big and complicated subject. So I'm going to start out with Mother Nature. As Ralph said, I was a planetary scientist, and this is actually how I got into what I do, was thinking about why does a planet have the climate that it does. So basically every planet has a climate determined by solar in, by energy in minus energy out. The energy in is the amount of solar radiation falling on the planet, and then minus the part that's reflected away. So you can see that down here in this little equation, and I promise not a lot of equations, but this is the cross-section of the planet, the solar radiation at the planet, at the radius of the planet, and this is the thing called an albedo, which is just the reflectivity of the planet. That energy being absorbed has to be balanced by the energy lost, which is this nice 4 pi r squared, and then sigma t to the square, t to the fourth, where that t is just an equivalent temperature. If you solve this equation for the Earth, you get that the average temperature of Earth is 255 Kelvin, or minus 17 degrees centigrade, which is right around freezing Fahrenheit. And your first thought is, what are you talking about? Because it ain't that cold. Well, this is the average planetary temperature, not the temperature of the Earth's surface. We would be in a world of hurt on this planet's surface if we didn't have an atmosphere, and that atmosphere has a greenhouse effect. So what happens is energy is emitted from the surface, absorbed by the atmosphere, and then re-emitted back down towards the surface. And it's this combination of radiation from the sun and radiation from the Earth that keep the planet temperature at a reasonable place. Also, it would be incredibly cold at nights, and it would be incredibly cold in the winter. You think Michigan winters are bad now, take away the greenhouse effect, and you'd be really in a bad place. So, as I just said, if you increase the greenhouse gas concentration, you're going to end up increasing the warming potential of the atmosphere. That's going to increase the downward radiation and warm the surface. And I will say, this is simple thermodynamics, and there is no way to buck the odds of thermodynamics in the real world. You can do it in movies, but you can't do it in the real world. One of the interesting things, if I try and put numbers on this, which you can see here, is that we get as much radiation on average at the surface from the downward radiation from the atmosphere over here as we get coming in from the sun itself, and twice as much as actually arrives at the surface from the sun. It is an important piece of our climate. What happens to all that energy is roughly about 25% of the, roughly half of the absorbed solar radiation ends up evaporating water and leads to those nasty things that Ralph mentioned, clouds, which became the subject of my study. Somewhere on this call is one of my graduate students, Sammy, and I are working on clouds in the tropical atmosphere, which has been an interest of mine for many, many years. So I haven't given up on this yet. I'm still trying to understand what they do. I want to mention briefly the global hydrologic cycle because this is going to come back. You can think of it, the global hydrologic cycle, as sort of a leaky bucket. So we have evaporation pouring water into the atmosphere, and we have precipitation taking water out here and there and everywhere. And there's no net change in the amount of water in the bucket. There's just water in and water out. However, if we warm the atmosphere, the amount of water that we can put in the bucket, called the atmosphere, goes up. And that's a simple result of chemistry, something called the Clausius-Clapeyron equation, and very simple thing. Now, that doesn't guarantee, just because you raise the amount of water in the bucket, that you're going to get more water in and out of the bucket. But it turns out, for good reasons, which I'm not going to get into, that's in fact what happens. As we warm the atmosphere, we increase the cycle rate for the global hydrologic cycle, which means we end up with higher rain rates, more rain events, more water coming out, and also, of course, more evaporation to keep the balance. So let's start talking about messing with Mother Nature. This is a simple diagram. I hope there's at least a few people in the audience who are interested in spectroscopy. Down on the bottom is a graph that shows from about 1 to 30 microns over here. And what you're seeing plotted on this scale is absorption in the atmosphere. So where you see the colors going all the way to the top of the atmosphere, or top of the graph, it means that if you inject a photon of that frequency, either at the surface, in this case, or at the top of the atmosphere, because this side is solar radiation and this side is thermal radiation, that photon has no chance of getting through the atmosphere. It will be absorbed. So if you look at this, you can see that solar radiation has lots of holes in it, where the solar spectrum has lots of holes where solar radiation penetrates all the way through. You get over to the infrared side, there's this kind of hole right here, which we call the water vapor window, but lots of water vapor absorption and lots of water vapor absorption over here. If we increase water in the atmosphere, we increase this absorption. This is the greenhouse effect, depicted in spectroscopic terms. Here's CO2. And CO2 is a much smaller absorption piece, but at a very critical place in the spectrum. And that we'll come back to why it's more important than water vapor in a minute. I also want to point out that there are a bunch of other gases that absorb thermal radiation and are important greenhouse gases, but all of these are smaller contributions than CO2 and water vapor, and they have a much shorter lifetime. The reason we're all perturbed about CO2 is that CO2, when it comes into the atmosphere, has a lifetime of centuries. Whatever we're putting in the atmosphere today is going to be there in 200 years and 500 years and maybe 1,000 years. Some of it's going to end up in the ocean, but the rest of it's going to hang around until it ends up being engaged in a weathering event with rocks. So this is why we're concerned that we're putting the stuff in the atmosphere and it's going to be with us for a very long time. So now a little look at CO2. This is a graph of carbon dioxide concentrations at Mauna Loa Observatory. This observatory, as you can see in the upper picture there, is on the flank of Mauna Loa at about 11,000, 12,000 feet. I went and looked for what the highest point in the lower part of Michigan is. The observatory is just a little bit higher than Briar Mountain, which is 1,700 feet. So this is way up there in the middle of, on the island of Hawaii, and we get to measure very well-mixed and clean air at that site. You can see the rise in CO2 going from about 315 part per million back in 1960 to somewhere up around 410, 450 part per million now. You can see this up and down wiggle, which is actually biology, Dana. That's the biology of actually plants in the Northern Hemisphere taking up and releasing CO2 over the annual cycle. We can look back further in time using ice core data, and this plot goes back about 1,000 years. And if you look at CO2 concentration, you can see that it was pretty steady here for quite a while. And that was around 280 part per million. Then it starts creeping up, and then it starts to really take off. And that's associated with the beginning of the Industrial Revolution and the burning of fossil fuels, particularly coal. This is kind of a cute graph. I like these because once upon a time I did think about really long-term problems. This is CO2 concentrations from 800,000, going back 800,000 years. How do we get back there? We use these ice cores. And now I like to say, well, we drill ice cores, but I don't really drill ice cores because that's really hard work. You have to go to Antarctica. You have to sit out in the cold. You have to drill giant holes. And you end up with slices like this. And these slices have air bubbles in them. The air bubbles are trapped in the lattice of CO2, and the molecules that are in those air bubbles cannot escape. So we can go back 100,000 years, 500,000 years, looking at the actual concentrations of gases that are trapped in these bubbles, and that's how you get this graph. We can extend this a little further using the Holocene, using more ice cores. Then we have the record that I just showed you for the last 50 years or so. So what happens in the future? Well, if we suddenly decided we were going to try and really stop putting CO2 in the atmosphere, we would get this. If we kind of stuck to what the Paris Accord is talking about, we would, by the turn of the century, be at maybe 670 part per million. Remember, we started out here at something like 300, so this is more than double. If we keep doing what we're doing now, we're going to be at 930 part per million. All right? That's like 3 times as much or more than what we started with. So what's the temperature been doing? Well, this is a graph of temperature over the last 150 years, mainly done with thermometers. And you can see that it kind of wandered around, little ups and downs, and it's really taken off the last 30, 40 years. We can go back in time, again, using global temperature, using temperature data from proxies. Proxies are things like tree rings, coral atolls, and the like. And you can see that we're much warmer now than any place we've been in the last 2,000 years or so. It's tough to go back much further than that because we run out of proxies. And it's not, we have some proxy records that go longer, but it's hard to make a global average out of them because you don't have enough to get a global sense. I want to show this just because I know I've got some physicists around, and this to me is just really cool physics. NASA has flown 2 satellites called Grace 1 and Grace 2, and Grace is a very high resolution, very accurate measure of the Earth's gravitational field as a function of position as the satellite orbits. If you take the difference in time of these gravitational measurements, you get a change in mass. In northern latitudes, southern latitudes, polar latitudes, you can attribute that change to a change in mass. So if you think about the science of this and the technological sophistication to be able to do this, we can actually measure. And again, I say we in the royal sense, I have nothing to do with this, but we can get measurements of how much ice mass has been lost, how much melt has occurred in Antarctica and in Greenland. This just showed up on my radar screen recently. Climate scientists are a bit weird. We call normal the last 30 years average. Of course, that 30-year average has been shifting with climate change. So NOAA is about ready to put out its 1991 to 2020 normal, that 30-year period. If you take that data and you subtract the previous 30 years, so this is 2 30-year means shifted by 10 years, you get these 2 plots. You will notice that everywhere on this plot in the United States has warmed except for just this little area up here, which is sort of no change. So just in 30 years, we have a demonstrably warmer United States. Precipitation's a little more interesting. This part of the country has warmed. This part has gotten wetter, and this part has gotten drier. And this is consistent with what we understand about climate change and how warming climate is going to work with enhanced CO2. Places that are normally wet actually get wetter. Places that are normally dry get drier. And this is part of that acceleration of the hydrologic cycle that I talked about a minute ago. So this is all consistent. It's also disturbing because this is looking like a long-term transition to a drier, more hostile climate in the southwest of the United States. Okay, let's jump to the future. We could have a whole talk just on this subject, but we're not going to. I simply want to point out that if we take our climate models and we start them back about 1900 and we run them along this track, using the inputs that we have, we get this. And then we start venturing into new and unknown territory somewhere around 2010 in these runs. And you can see that this run is warming a lot. This is the business as usual. This is pushing towards 1,000 parts per million of CO2 here. The temperature change globally is about 4 degrees centigrade or 8 degrees Fahrenheit, which is as much change as between the current interglacial and the last glacial period, only in the other direction. This is an enormous amount of temperature change for climate. Even if we try and aggressively transition to green energy, we sort of do the Paris Accords and a little better, we're still looking at something like 2 degrees. The physics in these simulations is not the question. The question here, by the way, is the scenarios. It's what are we as a society going to do about our energy use? So we can make a diagram like this, which gives projected impacts of climate change. And up on this axis, you have temperature change 1, 2, 3, 4, 5 degrees C. So far we've done this kind of right through about 1 degree. We expect to be at something like 2 degrees, probably at the rate we're going by the middle of the century. And if we don't do anything, we're going to be out here at 4 to 5 by the end of the century. So what are we talking about? Well, in agriculture, we're talking about falling crop yields. Some places in high latitudes may get a bump. So if you're growing wheat in Saskatchewan, you might be looking at a good thing. But if you're in the tropics, you're in big trouble. Fresh water is going to disappear, not disappear completely, but be in places a lot harder to get. And we're also going to see significant sea level rise, probably at a minimum of 1 meter by the end of the century, and quite possibly twice that. Ecosystem damage, we're already seeing damage to coral reefs. We're seeing other kinds of species extinction. Extreme weather events are going up. We see more intense hurricanes. We see rising intensity in lots of different storms, forest fires, droughts, and the like. This one is a little hard for us to say a lot about. The point is that as we drive the climate system towards a warmer environment, some things may happen that we can't go back. It's not a completely reversible system. So an example of irreversible climate change for right now are those gray satellite measurements, which is why I showed them to you. If we melt Greenland ice cap, if we melt parts of the Antarctic ice cap, we will not get them back. We are not going to get them back unless we have another ice age, and there's no indication that we'll ever have another ice age at these high CO2 concentrations. Another possible irreversible change is a change in the deep circulation of the ocean, which would be a pretty horrific thing to have happen. Okay, so if I go back, let's see, well, let me go back, come on. I want to go back here for just a second and remind you that we're talking about, something out here that's pretty drastic, 4 degrees. These kinds of changes. We kind of agreed in that as scientists that if we kept the warming to 2 degrees, maybe it wouldn't be so bad. And that's kind of where the Paris Accords were at. Now, we bailed on the Paris Accords for 4 years, but we're back now. And I want to read this little quote from a paper in Nature Communications. The author Walsh says, et al. Say, we find that barring unforeseen and transformative technological advancement, anthropogenic emissions need to peak within the next 10 years to maintain realistic pathways to meeting the COP21 emissions and warming targets. Now, that science talk, I'm going to translate it into the vernacular, which is, we find that barring a bloody miracle, we need to do something really drastic in the next 10 years, or there's no way we're going to keep things at 2 degrees. All right, is that clear? I hope so. These guys are saying, unless you have a miracle, we're going to have to do something starting now in order for us to keep this temperature change within 2 degrees and not get to the 4 degrees or more that we're talking about. So what do we do? Okay, right now we've kind of run through the basic science. We're going to take a little shift here. We're going to talk about what we do. So there are 3 things we can do. One is what we call adaptation. Basically, we're going to give up on the 2 degree limit, and we as a society, a global society, are just going to put up with whatever happens. Whatever happens, happens. We could start making really drastic cuts to emissions in the next 10 years, and we call that mitigation. In other words, doing things to mitigate the problem. Or maybe we can buy some time by cooling the Earth in the near term, which I'll call climate engineering. All right? A little clearer way maybe to think about this is my simple box diagram here of climate change. Over here, you have human actions that cause climate change. They go into the climate system, and the climate system then produces things that impact humans and the rest of society. So mitigation is getting back at this end. It's saying, okay, let's stop doing what we're doing to mess with the system. Adaptation is out on this end and is saying, oh yeah, we're just going to take whatever happens here and we're going to deal with it. And climate engineering is saying, well, is there something clever that we can do to the climate system? Mitigation, very briefly, is just about reducing emissions. You can see in this little blue curve in this diagram going from 1750 to 2020 that every year the amount of CO2 that we're emitting goes up. The annual emissions continue to increase. So if we think about mitigation, we have to think about mitigation in 2 steps. The first step is to reduce our emissions to the point where we're only emitting as much this year as we did last year and the year before and the year before. In other words, flattening out this curve. And then we want to reduce emissions each year to approach 0 emissions. So we want to drive this curve back here, and we want to do it in 2 steps. One is to flatten it out and then ramp it down. Okay? This is going to require structural change in the way we do. This is going to require structural change in energy production, transportation, agriculture, lots of things. Now, when I say structural change, I don't mean we're going back to the medieval period, all right? None of us are into that. But we're going to have to think hard about what we do. And some people at Princeton have given this some thought, and they have a nice conceptual way of thinking about it. So I've taken this from the Carbon Mitigation Initiative at Princeton. And they talk about this as wedges. Here's the current ramp we're on, and what they want to do is they want to apply a whole bunch of different wedge strategies to try and bring this down so that the goal in 50 years is that we're at the same emissions as we are today, all right? So this is their wedge strategy. Well, now let me put my own spin on it. What this means is there ain't no silver bullet. There might be some silver buckshot in these wedges, but there's no single silver bullet that's going to take us from where we are to where we want to be. I'm also going to tell you we don't have 50 years. We haven't got 50 years to wait around for this to happen. It's going to be too late. So this strategy has to get going now. What are the kinds of wedges? Well, the wedges include things like energy efficiency and conservation. They include things like fossil fuel-based strategies, replacing coal with natural gas, carbon capture and storage. We'll talk about that in a minute. Things you're familiar with, transition to solar, wind, biofuel, forest and soils taking up carbon. And yes, nuclear power is on here, and I think is part of the wedge strategy. Okay, adaptation issues. We can think about, well, we're going to live with this. And if we don't do anything else, that's always the default. We're going to live with it. But I want to point out there are just huge costs associated with living with it. One of the huge infrastructure costs is preserving all of the infrastructure that we have built along coasts. Think about what's going to happen if we start raising sea level and have more intense storms 1 meter or 2 meters. It's going to alter what it looks like on every coast in the world. And it's going to cost a gazillion dollars to move that stuff or to prevent damage to coastal cities. So you can think about what the Dutch do. It's highly interesting to go to the Netherlands and look at these structures they've built to prevent the ocean from encroaching. But you can also ask what it costs, and you can think about the coastline of the Netherlands and now extrapolate that to the coastline of the United States and go, oh crap, that's a lot of money. And it's a lot of effort. And some places you can't even do it because of the size of the river deltas. Then there's the whole issue of climate refugees. What do we do with climate refugees? Because there are people going to have to leave where they are. If we raise sea level 1 meter or 2, half the population of Bangladesh is going to be displaced. Where are they going to go? We're going to have tropical agriculture failure. How do we feed those people? Okay, so now I want to shift to climate engineering. Okay, we could talk a lot about the first part here of geoengineering methods, which deal with reducing carbon dioxide taking out of the atmosphere. Those are really good talk. That's a different talk than the one I'm giving. All right. So what we're going to do is we're going to talk about this one up here, which is solar climate engineering. Why am I focusing on that? Well, first of all, because I'm a climate scientist. And secondly, because the techniques for removing CO2 are not nearly as well developed and able to be scaled up as the solar climate engineering kinds of techniques. So let me give you a few ideas on how we might cool the climate to balance out global warming. Sorry, we're going to jump over the slide. Don't want to do this. So what's the role for climate engineering? Well, remember, here's the business as usual. Here's the idea that we're cutting emissions aggressively. Over here is some climate impact and time. And we're going to do this CO2 removal. And so we're going to peak here somewhere on these climate impacts, and then we're going to pull them down, pull the CO2 down. Well, this climate impact we're looking at here might not be so nice. Maybe this is 4 degrees centigrade change, and we don't want that. We want to limit it to 2. Well, maybe we could find a way to do solar geoengineering or climate engineering that would sort of take this peak out. So the point I want to make here is that anybody who talks about solar climate engineering has to be talking about something that is temporary. Temporary here being 40 to 50 years maybe, but temporary. We cannot continue to do this indefinitely. We always have to be working on the CO2 removal and process. Okay, so now, how about some ways to cool the planet down? Well, the easiest way would be just to move the Earth a little further away from the sun. All we need to do is move it a couple thousand kilometers a year, maybe a third of an Earth radius. Archimedes said if I had a long enough lever, I could do that. So I'm looking for some physicists to help me. Okay. Well, some of my former NASA buddies love this kind of thing. We could put up sunshades at the Lagrange point between the Earth and the sun, and they would just kind of rotate around, shielding us at all times from the sun. Turns out this is a really expensive solution. It has the really sort of fun thought process of what happens if you don't want the sunshades there anymore. How do you get rid of them? And that becomes the mother of all video games because you have to shoot them down or something like that to get rid of them. All right, so let's be a little more sensible, and we'll talk about looking at simulating volcanic eruptions. Mount Pinatubo erupted in the Philippines in June 15 of 1991. This picture was taken a couple months or a month or so later by the space shuttle, and it's looking across the limb, sideways across the edge of the planet, and you can see these big convective clouds pushing up from below. Well, you can also see these layers. These are volcanic aerosol layers. These volcanic aerosol layers cool the Earth, and we actually know that from the Pinatubo eruption. We can actually simulate them in models. So we know this works. So what we would do is create a synthetic volcanic layer. How would we do that? We'd use high altitude aircraft to inject particles into the stratosphere. These particles would spread around the globe, weeks to a month, spread around the hemisphere. So going pole to pole, in something like 6 months. They have an e-folding time of about 2 years, so they would all be gone in about 4 years. So we would have to continue to replenish this layer of aerosol in time. All right, all this is theoretically feasible. It's a little more complicated about whether you could actually do this. This is from a paper by a good friend of mine, John Dykema, who's part of a group at Harvard that works on this. So they proposed to do this experiment with something they call the Stratocruiser. This would be a set of instruments lofted on a big old balloon. They would lay down, the package would lay down a bunch of particles in the atmosphere. Then they would lift the balloon, motor it back, and drop the package, measurement package down and sample what had happened to these particles. How did they coagulate, disperse, all that good stuff. So this would be a precursor to starting to think about how you would actually do making the problem. This is an engineering issue, actually. So they proposed this to do this in the US. They were going to launch the balloon out of a place in Texas that we launch balloons out of a lot. They proposed doing this in 2019. It was delayed for technical reasons. In other words, something wasn't working quite right. They proposed then to move to Lapland in Sweden due to COVID restrictions in the United States. They scheduled this for the summer of 2021. It ended up being opposed by a variety of environmental groups in Europe, and their permission to do this experiment has just been revoked by the Swedish government. I have not talked to my friends at Harvard since I heard about the revocation, so I don't know what their plans are. My guess is we're thinking hard about what to do now, and probably going to try and do it in the US again. Marine cloud brightening, which is the problem that my colleagues and I have been working on, is depicted in this nice little cartoon from The Economist. It basically is the idea of adding salt to the atmosphere in order to create new little particles that clouds can form on. Now, this slide is probably the most complicated slide in the whole talk, because it's kind of half a semester's class of cloud physics in one package. Marine stratocumulus and stratus form at the top of the marine boundary layer, which means their cloud bases are typically about 800 meters, tops maybe 1 kilometer over cool oceans. Every cloud droplet, every liquid cloud droplet that forms on a small nucleus, a little atmospheric particle, which we collectively call aerosol in the atmosphere. These particles can be made of lots of different things. Many of them are slightly water. They can be salty. They can be basic. They are acidic. They can be organic, inorganic, lots of different stuff. The number of droplets that form in a cloud is directly proportional to the number of particles. It's not linear, unfortunately. That would make my life way too easy, but it is directly proportional. Particle population over the ocean is generally small. It's depleted because ocean our air is generally clean air. So what we can do is we can add more particles to this marine air, increasing the droplet number. The total water remains constant in these clouds because the total condensation is a part of large-scale thermodynamics and isn't affected by what you do at this small scale of making droplets. So you have the same amount of water, you make more droplets, the droplets become smaller, and if you do the radio transfer, you can show that more small drops reflect more radiation than fewer big drops. All right? We actually have an example of this. It's called ship tracks. These things that you see in this cloud deck are ship tracks. This, by the way, is California, if you can't quite see it under my. And what happens is a ship sails along, big old container ship, oil tanker, something like that. It emits stuff out of its stack. That stuff gets into the cloud deck, and sure enough, it makes these cloud tracks brighter. Okay, so conceptual view of marine cloud brightening as a project. We would identify marine clouds with limited nuclei that have limited nuclei available. We would add nuclei. So here's a cloud like that. We would add saltwater particles, spray salt water to add particles underneath that. They would get entrained into the clouds. They would increase the number of drops and change the cloud reflectivity. This works in my model. I'll come to reality in a minute. Conceptually, we would use a fleet of wind-driven robotic ships. This is an artist's conception of a naval architect's design. No such ship exists. Each of these ships would produce trillions of particles per second. And these particles would have lifetime of less than a week, so we need constant replenishment. So lots of little ships running around out here, constantly changing clouds. How do we see this happening? Well, this stuff gets done regionally, right? It gets done locally, so it provides local cooling. We can imagine that we would affect the regional climate system. So we might be able to selectively cool ocean over coral reefs. We might be able to cool the coastal ocean off of California to produce more onshore flow and moisture for coastal ecosystems like redwoods that are really suffering. We can produce global cooling by summing many regional cooling. So if we do this in many different places over large areas, we will end up cooling the whole globe. And again, our model suggests this is eminently possible. It's a little uncertain about how exactly you get from cooling these individual spots to a global picture. So we need a lot more research that involves a lot of numerical simulations and lots of regional tests of cloud brightening. So here's an experimental marine cloud brightening project for you engineering type people. This comes from a paper that I wrote with a colleague of mine, Rob Wood, and we published, as it says down here, in 2012. We need a sprayer, so we have to build a sprayer that will make really tiny, sort of 80 nanometer size droplets. We then would test this on a long coast and on a single ship, and then we would do an experiment that has multiple ships sampling kind of a 100 kilometer by 100 kilometer area, modifying clouds to show that we could do this. Okay, so we wrote this, pushing 8 years ago. Rob and I have been kicking this around for a decade. How come we haven't done anything? Okay, well, it's because we've had no government funding of any kind for climate engineering research in this country. Small sums were invested in Germany and in England, and they have been canceled. So there's basically no money to do this. A recent National Academy report suggests that we should spend $40 million a year for the next 5 years or so looking at this problem, which sounds like a lot of money, but trust me, it is completely inadequate for the scale of the problem or what needs to be done. So my point is, we are not doing mitigation and we are not doing climate engineering. So at this point, we're mostly looking at adaptation. We're going to live with what we get unless we get serious about looking at some of these alternatives. Just to give you an idea of what our nozzle looks like, again, for the engineering folks, this nozzle is making about 3 trillion particles a second, average size 100 nanometers. We would make a constellation of a sprayer would look like a couple hundred nozzles put together in something like these snow blowers. So putting out several 100 trillion particles per second into the boundary layer. We would test this, we would put it on a ship, shoot it out the back of the ship, and then we would do this kind of thing where we have multiple ships with multiple sprayers doing a big test. And this is the kind of thing where $1 million here and $1 million there doesn't go all that far when you start buying ship time and building sprayers. Okay, so now I'm going to move to the last part of my talk. I want to reframe this problem a little bit, and I want to talk about this particular view. So we can talk about science, which is can we do it? And we can talk about ethics, which is should we do it? And we can talk about governance, which is how would we do it if we wanted to do it in terms of international governance. And I am here to tell you that you can't stop with one of these circles. These 3 circles are intimately intertwined. I started out, the first time I got asked to do this by my colleague Rob Wood to look at this problem, I told him no. I said, I've already done nuclear winter and that got me in enough trouble. I didn't need to do more. Not too long after that, I got asked by a good friend of mine to come to a conference in California where they were going to talk about the ethics of people working on climate engineering problems. And I said, Mike, why are you calling me? And he said, you're one of the few people I know who think about science and ethics on these kinds of issues. We need you to come. So I went. Mistake. Because I got there and I got listened to what people were talking about, and I got totally scared about people just thinking they could just do these things without thinking about consequences. I went back home and I said to Rob, yep, let's get busy. 10 years later, we're still busy, but not making as much progress as I'd like. One of the things I've done the last few years is I've twice taught a class with Steve Gardner. Steve is a colleague of mine at the University of Washington. He's an environmental ethicist in the philosophy department. He is a brilliant guy, and I have just totally enjoyed teaching, co-teaching with him a class on ethics and science of climate engineering. I have learned a ton, probably just as much as the students. In his book, Steve lays out 3 aspects of a perfect moral storm. The first one is that climate change is a truly global phenomenon. Unlike most ethical issues, it doesn't have any global boundaries. Once you emit a greenhouse gas, it goes everywhere and everyone is affected. This is the biggest tragedy of the commons you can imagine. The tragedy of the commons is when people all use an asset, but they don't own it. They share in its value, but they don't own it, and therefore they have no real reason to maintain that asset. So how do we get people to care about shared assets that none of us own when they're global? There are skewed vulnerabilities here. Many of the most vulnerable countries and people are those who have emitted the least or are now emitting the least CO2. The poster child at the moment is an island nation called Tuvalu, where sea level rise and land shrinkage is driving them out of their homeland. There will be no Tuvalu for them to live in another 20 years or something like that. So what are we going to do? The second challenge is that current emissions have profoundly intergenerational issues. It is hard to think of another ethical challenge where we are talking about what are we doing to our children and our grandchildren. How do we quantify or even consider the impacts of what we're doing now to generations that have not yet been born? What are my obligations? The third one, which may not be so apparent until you think about this for a little while, is that we don't have the theoretical tools that we need to understand how to address this issue. We simply have not thought about these issues. We haven't created some sort of foundational level of understanding. What are the issues? What are our moral value, our moral values towards protecting non-human animals, unique places or ecosystems, nature? We talk about that once in a while, but we really have an undeveloped understanding of that. How do we understand scientific uncertainty, not uncertainty in the science, but uncertainty in these projections and where we're going and how this is all going to work out, the potential for catastrophic outcomes. Economic models don't deal with this. They don't know how to deal with this. They have this wonderful thing called the discount rate. We don't even know what the discount rate is for this problem. So we are in a real sad shape here in terms of understanding this. And I want to make just a little aside here. This is a place where I wish the Christian community were speaking loudly and clearly about how we should think about these problems. And what I hear is crickets. There is simply nothing going on. Okay, some ethical considerations now about each one of these topics. I want to start with climate engineering. Climate engineering represents a particularly nasty set of ethical considerations. So there's this thing, and this is just a sampling. This is this thing called moral hazard. Moral hazard is when you supply a technical fix to a behavioral problem and therefore allow people to excuse their behavior. So we're saying the real behavior problem is emitting CO2. We really ought to stop that. But I'll give you a technological fix. I'll help you do solar climate engineering, and then you don't have to stop doing what you're doing to get us in trouble anyway. This one of hubris is great fun to think about. If you're into Greek mythology at all, there's this guy Prometheus, and Prometheus steals fire. and gives it to humans. And the gods are really upset because the humans are not supposed to have fire. They are simply not able to deal with this. All right. Then there's a guy, Icarus. And Icarus is the guy whose father, Daedalus, makes him exiled to an island. And Daedalus makes wings out of wax and bird's feathers. And they're flying off the island, and Icarus gets too excited about what he can do with his wings. He flies too close to the sun, the wax melts, and he falls to his death. All right? So hubris, when you think about climate engineering, are we talking about Prometheus, which is we should never do this? We should never play God no matter what? Are we thinking about Icarus? We're just not smart enough yet? We shouldn't be thinking about how we do this because we don't understand the climate system well enough? Then there's this guy over here, the lesser of two evils. Often when I talk to people about climate engineering, they go, well, you shouldn't do that because you don't know what you're doing. And I go, yeah, well, we're doing climate warming pretty much without knowing what's going to happen either. And I can make a pretty convincing argument that the outcomes of solar climate engineering are going to be less of a problem than the outcomes of global warming. So what we're facing is not a do no harm issue. We're facing a lesser of two evils, which is the infamous trolley problem, if you're a philosopher, about is it okay to do evil, even if the outcome is lesser than what you would accomplish by not doing evil? Is it ever possible to do evil, philosophically speaking? And this is a real nasty question when you start pulling it apart. This one here really involves management as well. If we're going to talk about doing climate engineering, who pays for it? Who's responsible? Who determines what the climate is? At this point, I always go back to wintertime in my house. We have a thermostat, and there's only two of us at home now, my wife and me. The kids are all gone. And so one of us turns the thermostat down, and one of us turns the thermostat up, and one of us turns it down, and one of us turns it up. Who gets the right? Well, my wife tells me she has the right to turn it down because she pays the electric bill. Maybe she's right. We're still debating the justice here. What about this guy? Oh, I jumped ahead. What about this intergenerational issue that I've mentioned before? What is our obligation to the future? Well, we could spend a lot of time talking and reading about these. I want to briefly touch on ethical issues of mitigation and adaptation. Mitigation really raises issues of international justice as who's responsible and who pays. If we're going to develop technology that enables us to get off of fossil fuels, who owns that? How do we make sure that countries that are simply starting to develop their energy needs get that technology at no cost? Economic justice. How do developed countries ensure adequate growth for developing countries while reducing emissions? Technological justice. Who owns this technology? Who should profit from that ownership? You know, this country is always big on private ownership, but does that give us the right to exploit other people? And if you want a good example of that right now, think about the pandemic and who's getting COVID shots and who's not getting COVID shots. Adaptation raises these issues of intergenerational justice. What are we leaving to our children and how do they deal with this mess? My friend Steve Gardner is really concerned about this whole issue and is trying desperately, and I don't mean desperation in a bad way, to think about figure out how do we talk about this? How do we think about it? What's the approach? International justice, how do we deal with displaced people? At this point, I want to point out that we think we have problems on the southern border right now with Mexico. Wait until we start having drought and more storm damage in Central America and Mexico. Where are those folks going to go? They're going to head north. So we can think about maybe building a big tunnel to Canada, run them underground and have them pop up in Canada, and then we don't have to worry about them. Canadians might be upset with that. Stewardship. What is the value of ecosystems and species that are destroying or decimated by climate heating? What do we do? Okay, the bottom line, winding up. We have a very good grasp of how our climate works. Climate change has changed over the past 100 to 150 years and is changing now more rapidly than it is compared to any change in recent history. Projections of climate change over this century are dependent on the emission scenario. They're well understood in terms of direction and global magnitude, less understood in terms of precise magnitude and regional variability. And some of the outcomes are pretty scary in terms of their potential impacts. The science is sound. The science community is hugely in agreement. And I just added an asterisk on this slide today. I have just noticed an uptick in the number of naysayers out there. What's happening is the fossil fuel industry is seeing that we have an administration that's taken the whole problem seriously. We've rejoined the Paris Accords. We're talking about different kinds of infrastructure development. And all of a sudden, there's a bunch of people saying this isn't going to happen. The scientists are wrong. No, don't be misled. Bottom line in terms of ethics is pretty simple. Our choices are limited. We can change our behavior. We can adapt to the consequences, or we can try to engineer our way out. Climate change involves ethical issues, not just scientific issues. I'm very fond of the statement that a budget is a moral document. Anytime we sit down and ask how we spend our own money, how we spend the money of an organization that we might be associated with, there are moral choices that are going on in that budget. Well, a climate change plan has moral issues involved in it as well. And we need to recognize that it's not just about what we decide for ourselves and for our own little place. Climate change will be felt most dramatically by the younger generation, not my generation. And I'm going to tell you a little story here. We have 3 children, and my middle daughter has always been the speaker of truth in the family. If you want to get the straight opinion, ask Jen. A while back, maybe about 15 years ago, my wife and I were fortunate enough to be able to buy a place on one of the islands in the Sound, and our piece of property is right down on the beach. The floor of our house is 4 feet above high tide mark. So we bought the place, and my daughter and son-in-law who live here in Seattle came out to see the place, and my daughter's walking around looking at all of this, and she said to me, "Dad, I don't believe this. Don't you believe in climate change?" And I look at her and I go, I look at her and I go, sea level rise is a slow thing. You know, I've got 20 years before I have to worry about it. And by that point, I won't care about it. It'll be your problem. She stopped cold for about 10 seconds. And then she looked at me and she says, "I don't like that answer." Well, I want to tell you that answer is right. It's not my problem. In the sense of, I'm not the one who's going to be affected by it. It is my problem because I care deeply about it. But it's the younger generation that's going to face this. So what can you do? Well, sure. I want to tell you to change your personal behavior. Get your family and friends to do the same. Think about how you get around in the world. Think about how you spend your money. Think about your carbon footprint. I would love to be giving this talk in person, but I do realize that there's a lot to be said for me not getting on an airplane and flying to West Michigan, even if it means I can't see my grandchildren who live in Michigan. So think about that and do it. But we cannot solve this problem by our own personal actions. And I know this goes against the grain of all of the independent view of Americans. But this is something where we need to work societally. Vote. Contact your legislator. Go to their offices in town hall. Use your institutional power, university group, local political group, church group. Use that power to influence what your legislators do. I followed the election in Grand Rapids with some interest because Hillary Skolton, who is running against Peter Meyer, is a friend of mine, and I had hoped that she would win. She did. Peter Meyer did. But you have an opportunity to go influence people like Fred Upton and Peter Meyer who are at least serious about this. I don't know if you can actually get to some of the other legislators to make them think about it. influence federal politics. I'm talking about federal politicians mainly because I know them, but I should have been mentioning your state legislators. Influence your federal politics. Do the same things. Use your institutional power collectively to make government do the right thing.
I think I'd like to urge our audience to give you a round of applause, either by way of signaling such or by physically clapping. So I'm going to do the latter, but we're very glad you could come, Tom. Well, thank you so much.
Thank you very much for the opportunity to speak. I know sometimes students are reluctant to ask questions. They can always email me. I am not the most reliable email person. One of my former postdocs said I was a black hole. Things went in and never came out. But I will try and answer.
Great.
Thank you very much.
Thank you.